variables or state parameters. Thermodynamic properties are of two types. One, intensive properties, which are independent of the mass of the system. For example, pressure, temperature, density. And two, extensive properties, which are related to mass. For example, volume, energy, enthalpy, entropy. When we know these properties, we can describe the state of the system. If these properties change, the state of the system changes. Thus, we have learned the concept of heat, thermodynamic work, internal energy and thermodynamic state.
Now let me discuss the first law of thermodynamics, where it is used and what's the importance of that. So before that, what's energy? Energy exists in many forms such as mechanical energy, heat, light, chemical energy, electrical energy. So many forms of energies are there. Thermodynamics is the study of energy, and first law of thermodynamics represents the conservation law of energy or law of conservation of energy. Energy, it states that energy cannot be created or destroyed, but it can be transferred or changed from one form to another form, and the total amount of energy and matter in the universe remains constant. That is the law of conservation of energy, and this is the also the representation of first law of thermodynamics. Now first law is equivalent to the law of conservation of energy. It deals with the transformation of heat energy into work and vice versa, means work to heat energy. This is the statement of the first law of thermodynamics. When a closed system executes a complete cycle, the sum of heat interactions is equal to the sum of work interactions. Mathematically, we can write like this: sigma q, that is sum of heat interaction, is equal to sigma w, that is sum of work interactions. The summations is being over the entire cycle. Now this is the experiment set up for the first law of thermodynamics, and these experiments were conducted by the Joule in the year of 1843 to 1848, and for the basis of first law of thermodynamics. And the setup is like this: here pedal is there, a water is filled up in this tank, this is a temperature measuring device, that is thermometer, this is a pedal wheel, so it can rotate, here wheel is mounted, here pulley is there, and this is the load or weight, and this weight or mass moves. It can move from up to down, and according to movement of this mass, this steerer will rotate, this rotor will rotate, and accordingly this work can be transferred to this water. And this is the PV diagram for these two steps 1 and 2. Let me see how to work that. Work done on the system by lowering the mass m through Z1 to Z2, that is the change in potential energy of mass m. So this mass m is lowered from this first position, say here is 1 to 2, and hence its potential energy reduces. So its change in potential energy is equal to Z1 minus Z2, or change in its altitude. Then temperature of the system, after lowering this mass m from Z1 to Z2, it is noted that the temperature of the system increased, and the system was brought into contact with the water bath. Here water is there, so the temperature of water also increases, which was noted down in this thermometer. So rise in temperature indicates that the work is done and that work is transferred to heat. The system thus executes a cycle which consists of work input to the system followed by the transfer of heat from the system. Means work is given to the system and heat is exhausted from the system, and system was brought into contact with the water bath to have the thermal equilibrium. Mathematically we can write integration of dq is equal to integration of dw. This dq is from the system and dw is on the system, and hence integration of dq minus dw is equal to 0, or we can say q is equal to w. That means heat interaction is equal to work done, and the cycle is closed cycle. Now let me see one theory animation regarding first law of thermodynamics.
First law of thermodynamics. Objectives of the session: to study the Jules experiment, to state the first law of thermodynamics for a closed system undergoing a cycle, to state the first law of thermodynamics for a closed system undergoing a change of state. Friends, we all know the law of conservation of energy. It states that energy can neither be created nor destroyed, but it can be converted from one form to another. During the period 1840 to 1849, Joule carried out experiments on thermodynamic systems for analyzing the statement of conservation of energy. This led to the formulation of the first law of thermodynamics. Now let's see Joule's experiment. Observe the experimental setup. It consists of known mass of water in an insulated container having a thermometer and a paddle wheel. This forms a closed system. Now let a certain amount of work, say W12, be done upon the system by the paddle wheel. The quantity of work is measured by the fall of weight which drives the paddle. Let T1 be the initial temperature of the system, same as that of the atmosphere. After the work transfer, the temperature rises to T2. Thus, the system changes its state from state 1 to state 2. Next, the insulation is removed. The system and the surroundings interact by the heat transfer till the system returns to its original temperature T1. The amount of heat transfer Q21 from the system during the process 2-1 can be estimated. Thus, the system undergoes a cycle which consists of definite amount of work input to the system, that is W12, followed by transfer of heat Q21 from the system. Similar experiments were conducted by Joule for different modes of work transfer and for different systems. With the help of these experiments, Joule concluded that work input W is always proportional to the heat transfer Q. Mathematically, it is expressed as summation W equals J into summation Q. Here, J is the proportionality constant known as Joule's equivalent or mechanical equivalent of heat. This is also expressed as cyclic integral dW equals J into cyclic integral dQ for the closed path. Therefore, the first law of thermodynamics can be stated as 1. When a closed system undergoes a cycle, the algebraic sum of work input is proportional to the algebraic sum of heat transfer. 2. Also, the algebraic sum of total energy transfer as heat and work is 0. Mathematically, it is given as cyclic integral of d dash q minus d dash w equals 0. First law for a closed system undergoing a change of state. When a system undergoes a change of state during which both heat transfer and work transfer are involved, then the net energy transfer will be stored in the system. If Q is the amount of heat transferred to the system and W is the work transferred from the system, then the net energy transfer Q minus W will be stored in the system. This energy is known as internal energy. It is given as Q minus W equals delta E, or Q is equal to delta E plus W, where delta E is the increase in the energy of the system. Thus, energy is conserved in the operation. So friends, in this session, we discussed the Jules experiment, first law of thermodynamics for cycle and process.
Now applications of first law of thermodynamics.
Applications of first law of thermodynamics to an open system. In this session, we will study the applications of the first law of thermodynamics to an open system. Let us apply the first law of thermodynamics to an open system. The steady flow open system is defined as the rate at which mass flows through a fixed region. Such fixed region can be called as control volume system, and its surface is called as control surface. Let us study the mass balance for unsteady flow system. An unsteady flow system is a system in which the rate at which mass m1 flows into control volume is equal to rate at which mass m2 flows out of control volume plus rate of change of mass in control volume. Mass balance for steady flow system. Steady flow system is a system where the rate of flow of mass into the system is equal to the rate of flow of mass out of the system. Consider the flow of fluid through a pipe of cross-sectional area A, specific volume V at a velocity c. Then we get this equation is called as continuity equation. Now let us study what is flow work or flow energy. In order to move the fluid in and out of control volume of an open system, some amount of force needs to be applied. Let us derive the expression for work required to move the fluid of 1 kg in a controlled volume. Observe the cylinder along with the piston in inlet pipe. Let area of a system be A. Fluid inside the cylinder is at pressure P and the piston moves through distance L. Therefore, W equals force F into distance moved L. Thus, flow work or flow energy is the work required to move the fluid from the inlet into the system. Energy balance for steady flow open system. The following are the assumptions made in steady flow processes. 1. There is no decrease of mass in the control volume at any time. 2. The rate of mass transfer at inlet and outlet are equal. 3. The state and energy of fluid at inlet and outlet and in the control volume do not vary with time. And 4. The rate of heat and work transfers across the control volume is constant. The steady flow energy equation on unit time basis can be expressed as steady flow energy equation on unit mass basis can be expressed as steady flow equation on total time basis is given as steady flow energy can be applied to various engineering devices such as nozzles and diffusers, hydraulic turbines and pumps, gas turbines and compressors, boilers and heat exchangers such as condenser